In this segment, we'll look at how functions that take varying numbers of parameters, variadic functions, work. Now, like many languages, C lets you declare functions that have varying types and numbers of parameters. Printf and scanf are good examples. Consider these calls, for instance. Printf of value is and some integer versus printf of sum and average are and a couple of doubles. Each one takes a character pointer for the first parameter, but after that all bets are off. The first takes an int and then the second takes two doubles. In general, the parameters after the format string are completely unpredictable in number and in type, since they depend on the number and type of the format specifiers in the format string. Functions that may be called with many different types and numbers of parameters are called variadic. And the first interesting question is how one would declare a prototype or a header for such a function. The prototype for printf, for instance, would start with a character pointer parameter for the format string. But what would follow? There might be no further parameters, for instance for printf hello world, or as we just saw, any number and type of parameters. So the declaration of printf looks as in the notes here, int printf and then char star format with a ... after that. Recall, by the way, that printf does return an int. That ... is legitimate C syntax. It's not some abbreviation. It's the C equivalent of, whatever. You may pass any number and type of parameters that you like in place of the ... whether it's 100 parameters of varying types or none at all. Let's call these the variadic parameters, the ones that match the ... Now, importantly, as we'll see, there must always be at least one conventionally declared parameter before the variadic ones. One may not declare a function, in other words, to be just void f and then ... for the parameters. So, the ... notation lets you declare a variadic function, but when it's time to use the variadic parameters, for instance to print the ints or the doubles that were passed to printf, how do we refer to them? All we have in the function header is ... Well, the answer to this involves some serious runtime stack hacking in C. Variadic functions operate on the assumption that parameters are in a predictable pattern on the runtime stack. In other words, one after another. Since any variadic function has at least one normal parameter, the function can use this normal parameter's address as a starting point and deduce the locations of the variadic parameters from it. The variadic.c example in the slide does just this, on the assumption that parameters fall one after another in increasing memory order from left to right within the header, or the function call. Now, this assumption is valid for the GCC compiler that was used for the example, but it may not be valid for other compilers, and we'll discuss that in a little bit. And the function variadic here assumes, as a simple example, that it will be passed actually an int, a double, and a character pointer. So, question number 1, follow the math on lines 4 through 6. By how many bytes will the addresses in second pointer and third pointer differ? How many bytes apart will they be, and why? If you work through the math there, coming back from a pause, you should conclude that they'll differ by 8 bytes, because third pointer is derived by adding 1 to second pointer, thus, but that adds the size of a double, or 8 bytes, because second pointer is a pointer to a double. As the output on line 21 shows, this works, with the pi and high parameters being correctly pointed to, apparently, by second pointer and third pointer in the printf here. The associated diagram shows why, assuming the order of parameters that was described in increasing memory order, the pointer logic on lines 4 through 6 point second pointer and third pointer to the pi and high hi, or the pi and high parameters, respectively, with each addition of 1 to the prior pointer parameter skipping past that pointer's parameter to the next one in order. As long as we know the types of the parameters, this method will work with any number of variadic parameters. In the case of printf and scanf, the format strings give the type and number of variadic parameters via the format specifiers within them. Printf and scanf use their format strings to guide the pointer arithmetic needed to retrieve the variables corresponding to each format specifier. Other variadic functions may deduce the type and number of their variadic parameters in other ways, but they must have some means of doing so in order to use this RTS hacking approach. Now, note that pi is a float variable, not a double. On line 15, which we just discussed, we cast it to the correct type. But on line 16, we don't. And yet, the output of that second call remains correct on line 22. Now, based on the discussion thus far, this should surprise you. Why is it odd that this second call should still work? What would we expect might go wrong with it? Coming back from a pause there. Well, it's because float is 4 bytes, while the double is 8. And thus the second parameter on line 16 should take only 4 bytes, which would completely throw off the address calculations on lines 4 through 6, which assume an 8-byte double for the second parameter. In other words, instead of the layout that we actually had for the first call, we'd kind of expect what we would get is something like that, which, of course, does not line up properly with the logic of pointer arithmetic that assumed that the second value would be 8 bytes instead of 4, and everything would be thrown off. With second pointer pointing to the combination of the second and third parameters, and third pointer pointing past the end of the parameters, in fact. So definitely not a good outcome. The second call does work, in fact, because of a special parameter passing rule for variadic parameters. As we saw, getting the types of variadic parameters even a little bit wrong, for instance float versus double, badly messes up the delicate pointer arithmetic that the function uses to retrieve the parameters. To reduce the risk of this, C promotes all small types passed as variadic parameters to their full-sized equivalent. Specifically, it promotes char and short to an int and float to double. So line 16 actually is passing a double, appearances notwithstanding. You get the double cast for free. But line 17 is not passing a double. The second parameter there is just a 4-byte int, which is passed unpromoted. The result on line 23 serves as a cautionary tale about getting variadic parameter types right. Clearly, the second parameter is messed up in the line 23 output. But why doesn't the compiler catch this as a type error? Because the matching formal parameter in variadic is just ... offering no information for type checking. And the compiler isn't going to pick apart the pointer logic on lines 4 through 6, trying to figure out what's expected. With variadic parameters, there's no type checking. It's all on the honor system, with ample opportunity for interesting bugs. And on that point, here are 2 questions about that call on line 17. What exactly does get printed as the second parameter value? What does second pointer end up pointing to and treating as a double exactly? So, coming back from a pause, I've added a diagram up here that shows what will be passing, the 42, the 3, and then a pointer to the string hello. And so the result here is that second pointer points to 8 bytes formed by the integer 3 and the pointer address in high. Now there are a lot of 0 bytes in those 8 bytes, and the result is either a double precision value of 0.0 or one that's very close to it, which is why we get a 0 in the output. Okay, well, that's bad enough. But then why did the hello get printed anyway? To answer this, you need to think back to earlier RTS discussions and be clear that nothing was passed for the third parameter in line 17 because the 3 and the high parameters got treated collectively as the second parameter. What did third pointer then point to? Coming back from a pause there. Well, third pointer would have pointed to the next 4 bytes in memory, which generally would be random data. But in this case, it's going to be the leftover third parameter from the prior call on line 16. Remember that the stack frames for the 2 calls will occupy the same area of memory. And what you should get from these 2 questions is an informed fear of messing up variadic parameters. The Wild West variadic anything goes is nice until you realize how subtly you can shoot yourself in the foot with it. And this is compounded by the fact that 2 of the most common C library functions, printf and scanf, are variadic. By the way, question 5 here. Speaking of printf, why do both %C format specifiers in the printf below here work, printing A each time? You can try it if you doubt me. It does work. Printf does let you pass an int to a %C format specifier, assuming the int contains a valid ASCII code. But since the char and the int are passed variadically, how does printf know to expect 1 byte for the first one and 4 bytes for the second one? I'll put that up in the notes here too, just for reference sake. Pause and think about it. And coming back from the pause there, the answer is that printf doesn't know the difference, and it doesn't need to, because you can't pass a character to printf. The AC is promoted to an int automatically. So the %C format specifier always expects an int, and always has. It never expects a char. So to summarize here, first, for variadic parameters, the type checker is you. And second, omitting a variadic parameter or accidentally passing too few bytes results in the recruitment of random bytes following the real parameters. And sometimes, unluckily, these actually sort of work, as with our third pointer, since they're leftover parameters from earlier calls. And point 3, you cannot pass chars, shorts, or floats to variadic parameters, no matter how hard you try. They get promoted to ints, or doubles. Let's close here with a little bit of C history that bears on this discussion. In the original C, by which I mean between 1970 and 1989, even non-variadic functions followed variadic-like parameter rules, in that there was no parameter type checking. The function would declare parameters explicitly, so there was no need for pointer arithmetic, but you could pass anything you wanted, at your peril. And the variadic small promotes to large rules we just discussed applied to all parameters, not just variadic ones, as in modern C. Even a modern C compiler will do this kind of function call for you, or to you, if you write a function using the old style header. And looking in the notes, or the transcript I should say, you can see that we have first int f passed 3 parameters as a standard modern function header. But then down below is what I describe as a nasty disco era function header. And we've got the parameters listed there, ADS, but their types are given as a sort of extra local variable block before the opening curly brace, and that's the old style of function header. If you ever see the latter one, be aware that you're looking at really old code, and variadic rules will apply. If possible, revise such code, and of course, never write it yourself.